calculus-wise, anyways. Not that I don't care about the rest of your lives, but I don't have a lot of impact or control over that. I can help you with the calculus part. Yeah.
So how do you do 7b?
In section 2.1 or 2.2?
It's going to be in 2.1.
Okay. So in question 7, you're given like a table, and that table has a bunch of times and then displacements, like distances traveled. And in part A, it asks to find the average velocity for a couple of different time intervals. And in part B, yeah.
I don't remember exactly what I had so much trouble with. I marked it a bunch. I lot.
It's
so
okay.
Something happened.
It's one of these that there's a bunch of different ways you could approach this with a bunch of different like reasonable things you could do on this. In part B, it says use the graph of the function to estimate the instantaneous velocity when t is equal to 3. So I think there's probably like 3 reasonable ways you could go about doing this. I think the most intuitive, and probably what I would have done given the information that was provided in the question, is I would have taken the average velocity from 2 to 3 and the average velocity from 3 to 4 and just averaged those two numbers, which would probably give me a fair estimate for the instantaneous velocity at 3. Is that okay?
Yeah, that is. Yeah, that makes sense.
Okay. Another thing that I could have done is I could have plotted those points, so like those times and displacements, on my calculator, used it to build some kind of regression curve, and then use what we did on like the very initial example for this. Like we did the example in this question, or in this problem where we looked at the instantaneous slope or the slope at the 0.11 for x squared. You could have done the same sort of process, but that would have been like, I think, a lot of hassle, but you could have done it that way. And I think even reasonably, you could have like gone ahead and plotted the points and like sketched a curve in there and just like eyeballed a tangent line and estimated the slope from that. Would have probably been okay.
Okay.
So any one of those 3 ways to approach that, I think would have been fine.
Okay.
I probably, like I said before, I'd probably just take the 2 average velocities and just take their average, because it's not a lot of work to do. You know, like what is it? 46 minus 20.6 is the first average velocity, and 79.2 minus 46.5 is the second average velocity. And just take the average of those 2 numbers, and I think that'll give you a pretty fair estimate. Does that make sense, Blake?
That does make sense, yeah.
Now, this problem, because all we have is the table, that's kind of the best you can do, is to just take the 2 average velocities that you can calculate that are on either side of that desired value and just take their average. Yeah.
How do you find average velocity?
So average velocity is just like a slope, basically. So it's just the change in distance divided by the change in time. Does that feel cool?
Yeah.
It's just basically a slope, where you think about each column in your table there as a point.
Do you mind just doing like 5A and then like the first one, just as an example?
Sure. So it says if a ball is thrown into the air with the velocity of 40 feet per second, its height in feet t seconds after it is given, or t seconds later is given by y equals 40t minus 16t squared. Find the average velocity for the time periods beginning when t equals 2 and lasting 0.5 seconds. Okay? So basically, what I'm looking to do here is I would say, here's my function, 40t minus 16t squared. My average velocity then is just going to be the y-coordinate when t is 2.5 minus the y-coordinate when t is 2 divided by the change in time. So that's all I'm going to do. And that'll give me my average velocity for that time interval. The easiest way to probably do that is to just go and let's get rid of that right now. To type in 40x minus 16x squared into like my y equals menu here. And then I can just exit out. And in the main screen, I can just input this. Oops. So I don't have to worry about like typing all that mumbo jumbo over and over and over again. So I get negative 32. Does that feel okay, Luke?
Yeah.
Again, basically all we're doing is just calculating slopes, right? And then for this one, for part B, it says then estimate the instantaneous velocity when t is equal to 2. You're basically just looking at what's happening to those slopes that you calculated in part A and see if they're approaching a specific value. So they're going to keep getting closer and closer and closer to some number, and you're just trying to estimate what you think that number is.
So is that like what we did with the limits?
Yeah, it's exactly like what we did with the limits, yes. Does that feel better, guys, about the homeworks? Again, what you're actually doing, not that complicated. Understanding what to do and like why you're doing it is kind of the trickier part. But basically all these problems boil down to like doing a slope calculation or just like looking at the numbers and seeing what they're heading towards. Blake?
So on section 2.2,
Okay.
Question number 5, just in general.
Okay, let me take a look. Okay.
So I was able to get A, B, and I believe C, but I couldn't I don't really get how to do it because I couldn't get like the rest of them. Like
Yep.
I could get a couple of them, but I couldn't get all of them.
So I'm gonna just pause because we're gonna, like we just hadn't gotten far enough into 2.2.
Okay.
That's why you're having issues because we're gonna cover some of these major ideas here as to why the answers are gonna be what they are. And I think after today, that'll be much clearer. Is that okay that we just table this?
That's
Okay.
fabulous.
Okay. So good to know that like there's a reason you were
Yeah.
confused, and it's because we hadn't gotten far enough into 2.2 for you to really be able to do those. So that's okay. All right. That being said, let's pick up where we left off in 2.2. Does that sound okay? Okay, so I think the last thing we looked at in 2.2 was this guy. Am I right on that? Okay, this is where we had left off. We looked at this. And what did we say this limit was? Do you guys remember? Does not exist. So let's go back and take a look at that. just one more time to remind ourselves what was going on there. To turn that guy off. All right, and I'm going to zoom in real close to 0 here. Okay, that should be sufficient. Oh, and I guess I'd actually have the okay. And we have the I have the axes turned off here. Let's turn those back on for, well, maybe not. Let's just leave them off, I suppose. Let's do this for a second. I'm going to put this into degree mode real quick and just graph the same thing. Remember, what's the difference between the graph in degree mode versus radian mode? Well, it's like us zooming in at a lot, right? Because like 1 radian is like less than a 1 degree, right? So it's like, it's a really big zoom in. Right? And I think this one in particular is quite helpful in looking at this. So you see where the gap is in the curve? That's where x equals 0 is. So if I look at the left side of this curve, it appears it's going to, you know, some value there. But if I look at the right side of the curve, it appears it's going towards a different value. Everybody kind of see that? So this is, again, another justification for why that limit does not exist. Since if I look at it from one direction, it appears to be going to one value. If I look at it from the other direction, it's going to a different value. That's a problem, right? So let's formalize this. So let's call these two pieces. We'll call this number down here would have been the left-hand limit. And this number up here would be the right-hand limit. So if I'm looking at the line, the vertical line x equals 0, this is like the stuff that's happening on the left side. And this would have been the stuff that's happening on the right side. Is everybody okay with that notion? Okay. So let's write that down. This is how we're going to notate the left-hand limit. So we're just going to use that negative sign in the exponent. And to notate the right-hand limit, we're going to use that positive symbol in the exponent. Is everybody okay with that notation? And I think we used that briefly in last year in the Trig and Pre-Calc course when we talked about limits. We didn't do it a ton, but I think it popped up here or there. So let's think about this now for a minute based on this last example we were just looking at and these new definitions that we have for left-hand limit and right-hand limit. So what can we say about the existence of a limit based on the values of the right-hand limit and the left-hand limit. So what can we say about the existence of a limit based on the values of the right-hand limit and the left-hand limit? Amanda?
If they're like approaching the same limit, then the limit exists, but if not, then the limit doesn't exist.
Excellent. So for a limit to exist, the right-hand limit and the left-hand limit must agree. They must equal the same value, and that will then also be the value of the limit. So let's write that down as a lemma here. A lemma is just like a minor theorem. Okay, so we say the limit as x approaches a of f of x is equal to L if and only if the left-hand limit is equal to the right-hand limit, which is also equal to L. Everybody's cool with that? That was basically the observation that we just made. We've just formalized it into a definition. So let's look at an example here to kind of practice that definition. So I'm going to just draw ourselves a little picture here. So we should label that. Okay. So here's a little picture.
Is that bottom? X approaches, is that?
5.
Oh.
Is that cool?
Yeah.
Okay. All right. So take a look at the picture here that we've been given. What would we say the limit as x approaches 2 is? It doesn't exist. Excellent. Why is that, Amanda? Because the right-hand limit and left-hand limit are different. So the left-hand limit is going to 3. Oops. And the right-hand limit is going to 1. So we'd say then this limit does not exist. Does that feel okay? And Blake, this is almost like an exact example of the one you were asking about. So I think this example should help tremendously in doing that. How about the limit when x approaches 5? What is that limit? Paul? It's 2. If we look at the left-hand limit, that's going to 2. If we look at the right-hand limit, also going to 2. So this is 2. Notice, though, that f of 5 isn't equal to 2. What is f of 5 equal to? 1. Right? So the limit does not have to necessarily agree with the value of the function. That'll happen specifically in cases like this where we have discontinuities. Right? So f of 2 was undefined. Right? There's open circles at both ends when x is equal to 2. F of 5 is defined, but it's discontinuous. Does that feel okay? Doing all right still? Okay. So we've talked about left-hand limits and right-hand limits and how we can use those to determine if a limit exists. Right? We're going to move on and talk now about infinite limits. So let's look at a couple of examples. So let's start with the limit as x approaches 0 of 1 over x squared. If I were to ask you guys to evaluate what this limit is, what could we do? At this point, I think you guys have 2 methods to do this. You could look at the graph or look at a table. Either one would be fine. The graph is typically going to be quicker, so that's what I think we'll do in this case. I'm going to go ahead and turn the axes on my calculator back on. Turn this guy off. And we'll graph 1 over x squared. And I'm going to just do this on a standard window. Okay. So here's our picture. So if I look at my left end here, what does that appear to be approaching as x gets close to 0? Positive infinity. Okay, good. If I look at the right side of that function, what does that appear to be doing when x gets close to 0? Also to positive infinity, right? Everybody agree? The left-hand limit and the right-hand limit match. So what can we say? The limit exists and the limit's value is positive infinity. Okay. Now, if you had chosen to do this tab, using the table, Tegan. Sure. You are, my good man. If you had chosen to use a table to do this, so I would just do it this way. So let's do the left-hand limits first. We'll get progressively closer to 0 from the left. And you notice that as I'm getting closer and closer to 0, we're getting a bigger and bigger number, right? Which is consistent towards going to positive infinity. And if I did that with the positive values, I'm going to get the exact same numbers, not surprisingly. So feel pretty good about that, right? Limit going to positive infinity. Okay. Let's see if you can do this without actually using your calculator. What if we want the limit as x approaches 0 of negative 1 over x squared? It'll just be negative infinity, right? What will the graph look like? The exact same thing, but pointed down instead of up this time, right? Again, we can just, let me prove it to you or demonstrate it for you. So there's the graph, exactly as you guys suspected. Same thing as before, just pointing straight down. Okay. All right. Let's think about this one, though, for a second, once before we start graphing. What do we think this limit is going to be? The limit as x approaches 0 of 1 over x. Paul? So Paul says negative infinity. Well, let's think about this for a moment. If we approach 0 from the left, the numbers we're going to be using are negative, right? So if I plug negative numbers into 1 over x, getting closer to 0, that part of the graph is going to be going down towards positive or towards negative infinity, correct? If I approach 0 from the right, I'm going to have to be using positive numbers. As I plug those positive numbers in and I get closer and closer to 0, it's going to be going towards positive infinity. So we'd say that the limit does not exist. Right? So let's just take a look at the graph there real quick. Which is what we're seeing here, right? Anise?
When just x is the denominator,
Mm-hmm.
when you say most of the time it does not exist, because like, I'm just saying that because of the sign pi over x1, it didn't exist. Right? You just kind of
Ooh, boy, let me think. I'm not sure I'd want to say that. Because I bet if you did cosine of pi over x, I bet that works. I don't know. I'd have to think about it some more. Chillian, did I see your hand? Okay, sorry. Everybody okay? But that is a good observation that we've seen it a couple of times now. When the x by itself is in the denominator, we've had problems, right? But I hesitate to make that a always statement there. I'd have to really think hard about that.
what you were saying, yeah, so that, like, if I get it wrong in the test, I'd just be like, that's so cool that you told me.
Well, I just don't, again, but I think it's important that, like, we think hard about these things, because that's not a simple question you're asking. That's actually a really deep, complicated question. And in fact, I can already think of an instance where it's okay. So, where the limit will be, it will exist. So yeah, I would say no in general. That's not true, although it has been true in these couple of instances. And it's usually easy to build examples of things that don't exist when x is in the denominator by itself, but it doesn't do it by just itself. And we'll see some examples here later this chapter in which I can pull that out and
Okay.
come back to it. If you remind me, I'll make sure to.
Okay. All right.
Okay, Paul.
Can I use it back?
Sure. Okay, if we remember back and looked at or thought about the graphs for each of these three functions, what is going on at x equals 0 in the graph for each one of these three?
There's an asymptote.
There's a vertical asymptote. Great. So what do we think there is the relationship between vertical asymptotes and the limit behavior or the limit stuff that we're seeing here? Notice that when the limit was positive infinity, we got an asymptote. When the limit was negative infinity, we got an asymptote. And when the limit didn't exist, we got an asymptote. What is the key part to all of those?
Any graph with an asymptote has an
Okay. Except this one doesn't have an infinite limit, and it had an asymptote.
or an error, or there is no limit.
Well, you could have something like this. That wouldn't have a limit that exists, and there's no asymptote there. So the trick is you need to have at least one side of a limit needs to be an infinite limit. So let's formalize that. That'll cover the situation like we had in part C there, where the limit didn't exist. But both the left-hand limit and the right-hand limit were infinite. So, in fact, all we need is one infinite limit. So if any one of these three things is true, then there's a vertical asymptote at x equals a. So the limit at a is infinite, positive or negative. That would be enough. If the left-hand limit at a is infinite, positive or negative, that would be enough. Or if the right-hand limit at a is infinite, again, positive or negative, that would be enough. If any one of those holds true, then there will be a vertical asymptote at a. Everybody's cool with that? Let's do or look at a couple of examples just to kind of practice that now. Okay, so here we're asked to show that f of x equals 2x over x minus 3 has a vertical asymptote at x equals 3. So what do I need to do this? I need to show one of these three things. Okay? Any one of those three would be enough, though. So to start this, what do you think would be the easiest thing to do? I'm going to graph this and look at the picture, because that's the easiest way we have right now to evaluate a limit. So let's go ahead and do that. So there's my picture. Again, I would encourage you on this one to make sure you're using that fraction command to type this in, as it would require like a set of parentheses for both the numerator and denominator otherwise, and that's can be a little bit tricky, easy thing to overlook. If we look at what's going on at x equals 3, the left-hand limit is negative infinity, and the right-hand limit is positive infinity. Either one of those two by itself is enough to say we have an asymptote here, even though the limit itself does not exist. Everybody's okay with that? So all I would need to write here is say the limit as x approaches 3 from the left, and I'm just going to write f of x rather than write all those numbers, is negative infinity. Or similarly, you could just write that, also correct. Either one would be enough. Everybody's okay with that? Tegan?
So all you have to do is just show that one of them's infinite.
Correct.
Yeah.
Yep, that's it. Okay. So our next example asks us to find a vertical asymptote for tangent. Before I go and start graphing that, there is a trig identity that I would use here that would make this a little bit easier. What identity do we know? Tangent is sine over cosine. So what we're really interested in here is where cosine is approaching 0, or when cosine is 0. Yeah. Does anybody remember from last year what values on the unit circle cosine is equal to 0? Excellent. Pi over 2 and 3 pi over 2 are both situations where cosine is going to be 0. It doesn't matter which one we choose. I'm going to pick pi over 2. So I'm going to then be interested in the limit as x approaches either the left-hand side or the right-hand side of pi over 2. Let's go and take a look at the graph of tangent and see which one I would want to use. If it matters, maybe it doesn't. Oops. Why did I get nothing when I graphed this? I'm in degree mode. Good job. Easy to be like, Mr. Kulik, my calculator's broken. It's like, oh, I don't think it probably is. All right, and let's zoom trig this. If you press zoom and then pick the trig option, it'll reset your window from negative 2 pi to positive 2 pi with pi over 2 as the tick marks on the x, which is helpful. So here's pi over 2. So if I look, what's the left-hand limit of tangent at pi over 2? Positive infinity. And the right-hand limit of tangent at pi over 2 is? Negative infinity. So either one of those two would be sufficient. You don't have to do both of them, but you could do either or. So I'll just do the left-hand limit because we said that first. Yes, sir.
Could you go back to the graph?
Sure thing.
So why would the left hand positive?
Okay, so pi over 2 is right here,
Yeah.
correct? So this vertical line is pi over 2.
Okay.
So the left side of pi over 2, that part of the graph is pointing up towards positive infinity.
Okay.
And then the right side of pi over 2 is this part of the graph that's pointing down towards negative infinity.
Okay.
Does that feel good?
Mhm.
Excellent. Okay, so we've identified that pi over 2 is an asymptote and shown that it is one, right? Okay. So let's say the natural log has a vertical asymptote at x equals 0. Okay. So probably the natural place to start would be to look at the graph. Always an effective tool, provided you have a graphing calculator, which, again, on the AP exam, is that always going to be the case? No, right? I think we talked about that on day 1, that there's 2 sections. I should have Zoom standard this. There's 4 sections to your AP exam. There's 2 multiple choice sections, calculator, not calculator, and then 2 free response sections, calculator, not calculator. So the kinds of problems where you'd be evaluating limits using graphs or a table would likely be in the calculator section if they didn't provide those. But if they gave you the picture and they gave you the table, they could certainly be in the no calculator section as well, right? So it just should be able to do both. And then we'll see later on in this chapter as we go, there's algebraic ways to do limits that don't require the use of using any kind of calculator. And you don't have to provide it anything other than the equation and your own cleverness. Okay. So if we look at this, I don't know what's going on here. It seems like something is happening around 0, but I can't really tell. Maybe I'll turn my axis off and see what's going on. What do you guys think?
Does not exist.
Doesn't look like there's an asymptote, right? Well, this is the problem with your calculator. So remember, the calculator has only a finite number of pixels. So when things get very steep or are very not steep, you can get some weird looking graphs that aren't really indicative of what's going on. This is going to be one of those cases. So before you go ahead and say there is no vertical asymptote there, let's try using a table and seeing what happens there. Okay? Because according to this, it looks like at 0, it's settling down to some specific number, right? Everybody agree? Okay, I forget, which one was this? What slot did I put this in? 6. So real quick, let's just see what happens at y equals 0. Okay, so that's undefined. So not us, y equals 0 isn't just going to give us the answer like we did before where we just traced, what is the y coordinate at this x value. So let's see what happens when we go approaching that. So notice there was only one side of 0 that the asymptote was on. So we have to pick values that are positive. So maybe we'll start at 0.1. And then maybe we'll do 0.01. And then maybe we'll pick 0.001. It doesn't seem like it's settling down towards anything, right? They just keep getting more and more negative. All right, well, maybe I'll pick lots of zeros in 1. Still just getting smaller. Where do we think this is heading? Negative infinity. So here's a situation where the calculator, the graph that it was able to produce, is deceiving. That there is an asymptote here, even though it didn't look like one. And the table this time turned out to be quite helpful in figuring that out. Notice that this contrasted with when we looked at the limit as x approaches 0 of sine of pi over x, where the table gave us kind of the wrong idea, but the graph really was quite helpful for us. Really probably want to look at both in a situation where it's like, this doesn't seem like it really makes sense, or you're not totally buying what you're seeing, considering it's asking us to show that there's an asymptote here and it didn't look like there's an asymptote in the picture. Does that feel okay to everybody?
You have to add that plus sign, right?
Yes. If you had left the plus sign off, it would be wrong. Because the limit does not exist when x equals 0. It's only the right-hand limit that exists, because there was no left-hand side of the function. There's nothing left of 0. So the function is undefined over there. Not the same as negative infinity. Blake. Sure thing. All right, that closed out section 2.2 for us. I've had so many one-note stylus kind of problems this year. It's getting really frustrating. I think we're going to do a trip to the IT. I thought maybe it was just a low battery, and I went and got a new battery. It seemed to have really made much of a difference.
Well, they should give you new batteries for sure.
If you're a teacher, yes.
Right.
If you're a student,
Can you get me a battery?
no, but you could probably buy like a 10-pack on Amazon and have it delivered tomorrow for like $6 or something. And then you'd never have to worry about another stylus battery for the rest of your life. But I get it. So this will all go up on My Notre Dame also. In the assignment, I'll just keep updating it, just like we did last year in Trig Pre-Calc. Everybody's okay with that method that I used last year, where you just like keep getting parts of the assignment. I just kept adding them on. Again, today would be the last day for homework for Sunday's problem set. Anything we did Friday would go on to the next week's, so that you have a chance to ask questions about stuff before it's due. Right? Trying to be super fair. Everybody's cool? Feels good? Okay. Let's start 2.3. We're not going to finish this today, but we can start it. So up into this point, the only ways we've had to evaluate limits are with a graph and with a table, right? There is a third way we can evaluate limits, and that's purely algebraically, which is something that you will have to be able to do for the AP exam. Like a great non-calculator question is to be like, limit of blah equation, go. and you have no calculator to graph it. So you'd either try to be doing this by hand, which in a lot of cases is like really time consuming and unfeasible, or building a table out, which is no less of a problem because you're plugging in points and trying to like doing a lot of crummy arithmetic by hand, which is really time consuming. Or you can do these things algebraically, which usually go pretty well. All right. So we're going to start here by just kind of listing a bunch of limit laws or limit properties that we can use to allow us to algebraically manipulate these things. So I have this little preamble that applies to all of these. There's going to be 9 of these limit laws. So let's start. Suppose that n and c are real numbers. And are constants. And the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. I want to point out that these limits existing is crucial to these limit laws I'm about to write down being okay to do. The number one place where students are going to make a mistake is applying limit laws to functions whose limits don't exist and then getting all kinds of funky answers as a result. And we'll talk about in a little bit, maybe not even today, but we'll talk about some of the places that we have to be really careful about, but probably not yet today. So I'm going to call this law 1 and 2. So if we have the limit, oh my goodness, guy, as x approaches a of the function f of x plus the function g of x, that's equal to the limit of f of x plus the limit of g of x. So what's it look like we really did there? We just distributed the limit, right? So this is nice because you can take the parts of your function and evaluate the limit of each part individually, so you can look at simpler pieces rather than a big complicated whole. Sure. And I put /2 here because this obviously also applies if you're subtracting the two functions. Yes, Blake?
So going back to the thing of how it exists, is it like that both the actual function has to exist as well as the limit?
So the limit as x approaches a for f and for g have to exist for us to be able to do this kind of thing.
Okay.
So if you had one of them where the limit doesn't exist, you could do this kind of a manipulation. Be like, oh, look, now the limit becomes 0 or something for this f plus g. And it's like, oh, no. You can't be messing around like that.
Okay.
So you just have to be a little bit careful there. Now that's not going to come up right away, and we'll make a big point of that as it comes up a little bit later. Luke?
What is the notation for like n, c is all real numbers or equals all real numbers?
So they're an element of the real number. So they're just regular numbers, any number, as that's all we're saying. Limit law number 3 says the limit as x approaches a of c times f of x. So remember, c is a constant, right? It's just like a number like 2 or -8 or pi or 6/3. Well, 6/3 would be a dumb one. 7/3. What we can do is we can pull that constant out front of the limit. Which is nice because now we've just made the limit on the inside simpler, right? So if I want to do the limit as x approaches 7 of 2x, I can just do the limit as x approaches 7 of x and then multiply the answer by 2, right? Just allows me to make things a little bit simpler. The next one is the one that's rather surprising. So the limit as x approaches a of f of x times g of x you can do again as two separate limits and multiply your answer. That's quite nice, right? So suppose you had like the limit as x, or the limit as x approaches 0 of x times sine x, allows you to just do them one at a time, right? The limit as x approaches x, and the limit as x approaches sine x. You can look at things that are a little bit easier to handle. Again, making your problem, the function, much less complicated that you have to worry about. If you can do this for multiplication, obviously we can do this for division, right? And again, all of this obviously provided that g of x is non-zero. Oh, I shouldn't say that. I should say the limit of g of x is non-zero. Again, that shouldn't be surprising, right? So this one says if you're doing the limit as x approaches a of f of x to the n, that you can just do the limit of f of x, or the limit as x approaches a of f of x, and then raise that answer to the nth power. This is particularly helpful if you have like trig functions. So instead of having like the limit as x approaches 0 of sine squared, you can just worry about the limit as x approaches 0 of sine, take that answer and square it afterwards. So again, very helpful in making the function you're looking to take the limit of simpler which is it's the point of all of these limit laws, is it just helps you make that limit that you have to deal with simpler. Okay. The limit as x approaches a of c is, what do you think? This one should be kind of intuitive. The limit as x approaches 7 of the number 2. What would that be? It'd just be 2, right? 2 is always 2. Doesn't matter what x is. Doesn't depend on x. Just 2. So this would just be c. Does that make sense to you guys? Okay. So the limit as x approaches a of x, that is going to be equal to, what do you think? Right? If x is turning into a, as x approaches a, and all we have is x, that better be going to a, right? And then my 9th one here is similar to 6. So if 6 works for exponents, it should certainly also work for radicals. No. No, because because it just means 1 over, it's just the exponent 1 over whatever.
Yeah.
So it's still okay.
Oh.
So like if n was negative 3.7,
Yeah.
it just means it's to the power negative 1 over 3.7.
Okay.
So it just would turn into like 6, right?
Yeah.
So it's still okay. Doesn't necessarily mean it's imaginary. Where that part, if it was like n was 2 and you're talking about a square root, the place this would come in is if you had like the square root of x, x approaches negative 5, well, that limit doesn't exist, so you can't use that rule.
Yeah.
You know what I mean?
Yeah.
That's where that would come in. You know what I mean?
Yeah.
Okay. So let's do some examples now where we use these things. So this first example, I'll go through nice and slow and write everything out and kind of talk about what it is that I'm doing. All right. So the first thing I would do is I'm going to be using properties 1 and 2 to allow me to kind of distribute that limit to each of the 3 parts of this polynomial. Oops, that's a minus. Everybody's cool with what I did there? Okay. If I look at the first limit, what I'm going to use now is property 3 to move that coefficient of 2 out front. I meant for this to be squared, not cubed. Can I change that right quick here before we get too deep into this thing? That's not a bad place to do it now, right? Only have to change 2 or 3 things. As opposed to getting to the end and go, oh, fiddlesticks, that's not what I meant to do. And then have to resort through the whole thing. I'm going to do that same property on the second limit. So I'm going to use that to pull the 3 out front. And then I can use property 7 on the third limit. So limit as x approaches 5 of 4 is just 4. Since you're taking the limit of a constant, just the constant. So far, so good? Okay. On the first limit, I'm now going to use property number 6 to move that exponent outside the limit. And then I'm going to use property 8 on the second limit to replace that x with a 5, or the limit as x approaches 5 of x with just 5. And then I'm going to use that same property 8 on the first limit. So what do I got here? 5 squared is 25 times 2 is 50 minus 15 is 35, and then plus 4 is 39. So there's my answer. Does everybody feel okay with what I did there? Do me a favor though. Look at this line. What is that? I just plugged 5 into the function, right? That's a property, which is like the super property. This one is extraordinarily useful. This is the direct substitution property. Ugh, come on. Why is this being a poop butt? All right. So if f is a polynomial, or rational function, and A is in the domain of F, then the limit as x approaches A of f of x is just f of A. Yeah, buddy. That's pretty nice. All right. Let's do an example just to kind of practice that. Okay. Two things I need to check here before I can go ahead and dive right into this direct substitution property. What are the two things that the property requires before I can do this? Okay. Okay, is the function polynomial or rational? What do you guys think? Yes, which one is it? This is rational, because it's polynomial over polynomial, right? And the next thing we need to check is to make sure that a, in this case, -2, is in the domain of that function. What's the domain for a rational function? It's everything except where the denominator is 0. Is the denominator 0 when x is equal to -2? Then we're good. Okay? So, rational, check. I'll just write it that way. So, that's it. And just grind that thing out. So let's see. -8 plus 8 minus 1 is -1. And then that'll be over 11. Guys, is life good? Right? That's fantastic. That I can do. All right. Are there any other weird ways we can ask you to do questions like this? Sure. So instead of giving you a equation, what if we give you a graph? Oops, that's not where I want it. I want it there. Oops. So again, this is a favorite of like non-calculator kind of portioning question where they've given you something that was defined in a way that your calculator would be of no use to you, right? F of x and g of x are just defined with these pictures. We don't have an equation or anything that you could type in your calculator to help. What we'd want to do is use our limit properties to rewrite this as and then use our graph to evaluate. So f of x at -2. So there's my left-hand limit and my right-hand limit. That appears to be 1. And then to do g of x at -2, my left-hand limit, my right-hand limit appear to be -1. Still have that 5 there, though. So I end up with -4. Does that feel okay how I did that? So I just used the graph to evaluate the limits once I've separated out the limits to just on f of x and g of x. Should we do another? Let's do one more, eh? I think we got time for, what do we got? No? No more time? I don't know, we got 1 minute left of stuff. Let's just make a note to where this is where we left off and I'll come back. Okay.
That's hard. Trying to force it. That's less like that's okay. Trying to force it. Nah, this is gosh. I had to buy one anyway. I just forgot. That's the one thing. I forgot to go against the 2.3 for this. Dude, literally, this was the first.
We didn't get through enough of 2.3 for me to assign anything yet, I don't think.
I looked at all my old stuff.
Because I have, what do I got in my notebook here? I have like 2.5 more pages in 2.3. So I would say there's nothing worth assigning there. So Sunday's problem set will just be 2.1 and 2.2.
Or like you have a book or like
Yeah, so if you take that last tall cabinets, they're all in there. Grab one and come back.
It's gonna be a studious night.